Alright, last video on related rates, volume problems. I know a lot of problems we've already done have been about volume, so it's kind of a misnomer. Point is, there'll be some slightly hard ones, and we'll just make them a little bit trickier, even though there'll be situations we've seen in previous problems. We'll just make them a little bit juicier. Like, for example, look at this one. It's got a 20-degree angle in it. When's the last time you saw that? You haven't, right? That pretty much means we have to use SOHCAHTOA or like actual trig, not just one of these 30-60 shortcuts. So let's take a look. All right, we got cone volume. I don't know if we've seen that formula before. It tends to show up in this particular chapter, though, just because cones are a fun shape to sort of fill up. All right, so a cone, ice cream cone. Is conical real word? I think it is. Conical. With a 20-degree tip is being filled with hot fudge. All right, so it's similar to a problem we worked previously, except it's a pointier cone. So this is only 20 degrees down here. Being filled with fudge, so probably have a fudge level right there. Cone's not full all the way. The fudge's level is rising at 1 centimeter per second. Alright, so once again I think we'll have an h in here. So if dh dt equals 1 centimeter per second, when the fudge is 4 centimeters deep, how fast is fudge flowing into the cone? So this is a key point, is that when they're talking about filling stuff up, how fast something is flowing into the cone or filling up the tank or flowing in the pool, whatever, that rate of flow is dV dt. And of course we're not talking about the volume of the overall cone, we're talking about the volume of just the fudge we've already put in here. So they're asking for dV dt at this moment in time. So let's take a look. Now since I gave you this volume formula, you're probably thinking we should use that, and I'm thinking you're probably right. So volume equals 1/3 pi r squared h. So basically, if this, it's just the way I remember the volume formula for a cone is that it's 1/3 of what that cylinder would have been, because pi r squared h is just the volume of a cylinder, like a can of tennis balls or a can of Coke or beer or something. Just, you know, a cylinder with round ends would be pi r squared h. Put a third in front of it to take it to, you know, account for all the material removed to turn it into a cone. Alright, so we could take the derivative right now, we'd have a product rule, but it's doable. But the problem is that they've given us h and dH dt, but right now we do have some h's, but we also have r's. And I don't see any r's in any of my givens or any of my asked fors. So that means I want to get rid of the r's and replace them with h's. So now I'm going to do my trig. You know, if this cone is 20 degrees at the bottom total, that means it's actually 10 degrees for each half. Because here's h, here's r. So if you're looking from the perspective of this 10-degree angle, the sides, you know, are the opposite and the adjacent, not the hypotenuse, right? So from SOHCAHTOA, we're not going to use sine or cosine, we're going to use tangent. Because the tangent of 10 degrees in this case, you know, well, so TOA means tangent is going to be opposite over hypotenuse. So that means the tangent of 10 degrees is going to be the opposite side from there over h. So if we want to get rid of r and replace it with h's, we got to solve for h by multiplying both sides by h. Put that there. So we got r equals h times the tangent of 10 degrees. Now you might be tempted to get a decimal right now, and I wouldn't recommend that. I would just plug this in right there. So I get that the volume equals 1/3 pi r squared, oops, that was the thing I wanted to replace, pi times r squared, so that's going to be h tan 10 squared, and then times h. Alright, so we still haven't taken the derivative, that's why there's no dH dt's or anything yet. I'm still just trying to simplify this bad boy. So at this point we got 1/3, so we got pi, got kind of a big fraction, we got a pi upstairs, a 3 downstairs, total of h cubed, and we've got a tan squared of 10, which we'll just have to type into a calculator, obviously, since we don't know that one. And then they've asked for dV dt. So on the bright side, we don't have to rearrange the equation at all, we can just take the derivative at this point. So dV dt, which is what they asked for, is going to be, now you'll notice out of all this junk I have here, the only thing that's not a constant is the h cubed. So the constant, which is pi times tan squared 10 over 3. All that just stays out front. And then I've got the derivative of the h cubed to worry about, which is just 3 h squared dh dt. That 3 gets canceled by that 3. And now I've just got a lineup of stuff I can plug in. So it's going to be pi tan squared 10 times, now h we know, because they said when h equals 4. So 4 squared. And dh dt, they told us is 1. Alright, so that you're obviously going to have to type into a calculator, and I got 1.56 when I did that. What are the units? Well, let's see, we got centimeters. Now volume is centimeters cubed. And what is time? Looks like seconds. Alright, good stuff. Let's check out the next problem. Alright, spherical volume. What is a spherical volume? Well, it's just 4/3 pi r cubed, the volume of a sphere. And we're looking at a balloon. So we've got a balloon that's leaking helium. Now what does leaking mean? Doesn't that mean the balloon's getting smaller? So that's kind of exciting, a little bit different than other problems we've done. But the point is we've got a sphere that's getting smaller. So even if we hadn't given you the volume formula up here, you can bet we would have probably needed that one because it's pretty obvious we're dealing with the volume of a sphere. Leaking at a rate of 30 cubic centimeters per minute. So the given there is that the change in volume, the rate of change of volume, is going to be 30 cubic centimeters per minute. Alright, so how fast is circumference changing? Wow. So they're asking for d circumference around the sphere. Goes question mark when the radius 25 centimeters. Wow. Alright, so that hopefully everyone is now kind of on the same page on this, where it's like, holy smokes, I've got radius and circumference, not even radius and diameter, radius and circumference. Okay, so how fast is circumference changing when the radius of the balloon is 25? So I've got r, I've got dv dt. They're asking for dc dt, but obviously if I'm dealing with volume, there's really only one equation I can use, and that's the one up here. So we'll just write that down. V equals 4/3 pi r cubed. So if we took the derivative of this right now, we'd have a dv dt, we'd have an r, we'd have some r's like an r squared, which is fine, but we'd have a dr dt. And I don't want a dr dt, I want a dc dt. Huh. Alright, so I think the smart play is to switch this r to a c. So use substitution as we have done a couple of times now. So what's the difference between circumference and radius? Well, circumference just equals 2 pi r. Which means that wherever I'm in r, if I divide by 2 pi, 2 pi, those cancel, r equals c over 2 pi. So I can rewrite this as v equals 4/3. And then wherever I see an r, I can put a c over 2 pi. And of course that is still cubed. So what we've done is we've taken something that had r's in it and put in c's instead. And the reason for that is so that when we take the derivative of this formula, we'll have a dc dt, which is what I'm looking for. I'd really like to just pop out the derivative I'm looking for. So let's just simplify this a little bit more, because I got an exponent to worry about and stuff. So we got 4/3 pi times c cubed over 8 pi cubed. Now that pi is also cubed, which is a little bit weird. So we'll cancel that. This becomes a squared. And then this 8 becomes a 2, and that's a 1. Alright, so at this point we've got v equals, the only thing upstairs now is c cubed, and downstairs we got 6 pi squared. Alright, so is this something I can take the derivative of? Yes, it is. So v equals c cubed over 6 pi squared. Take the derivative of both sides, you get dv dt equals 3c squared dc dt. So that's just the derivative of the c cubed term. That 6 pi squared is all a constant, which is why I'm able to just leave this downstairs. Alright, that would be wonderful, except I'm trying to solve for dc dt, right? So I got to get dct by itself. So what I'm going to do is just multiply both sides by 6 pi squared over 3c squared to get rid of it. So dc dt equals 6 pi squared, just the the reciprocal, over 3c squared times dv dt. Whew. Alright, so at this point we're in a plug and chug situation, except for one little thing. I need to plug in circumference right here, right? Because when I switched everything to having c's instead of r's, that actually invalidated this thing. R equals 25 no longer has a place to plug in. Except I could just use the fact that c equals 2 pi r to find the circumference when r equals 25. So that's just going to be 2 pi times 25, which is 50 pi. So that is what I'm going to plug in for c down here at the bottom. Alright, so when I plug in everything, let's see, so I plug in that for c, I plug in for dv dt, I plug in 30. And I did all this on my calculator and I got 0.036. And what are the units? Well, let's see, they asked for how fast is the circumference changing, so that's a distance. So that's going to be centimeters, since this problem seems to be about centimeters. And the denominator, we're going to have either seconds or, minutes. Alright, so 0.036 centimeters per minute. Pretty good. Alright. These are brutal, right? Alright, last one. A modern art building is being constructed from triangular cross-section concrete beams. You see how far we have to go out of our way? Because like in real life, everything's either, it's either a nice cylinder or it's a rectangular box or whatever. But for these related rate problems, things that don't taper or anything are really boring. So that's why you'll find that we have to cook up a lot of really crazy sounding stuff in order to come up with triangular shapes that are being filled with liquids of various types. So I like the ice cream cones, and this time we're going to use a concrete mold. So it's kind of like an open top deal like this. It's a box with a triangular cross section, and it's literally being filled with concrete. So it's the concrete's just filling up from the bottom. All right, so that's the situation. We're filling a triangular trough thing with concrete. This thing is 600 centimeters long. Interesting. Horizontal beam is an inverted equilateral triangle. It's 50 on a side. So if I want to look closer, oops, it's a poor drawing. So there's 60 on a side. All right. My bad, 50. 50. All right, if concrete is flowing in the mold at this rate, so dv dt equals 1,000, how fast is the level rising? All right, so we've got the concrete's at this level so far, and we'll call that height h. So how fast is the level of concrete rising? So the reason I had to label that h was so I'd be able to write down that dh dt is our question mark. How fast is the level rising when it's half full? Now you notice they said half full, not what they would normally say, which is they'd give us a height. So half full, I'm going to interpret that, since I wrote the problem, as just meaning that we're halfway from nothing to top as far as distance. So if we zoom in a little bit here and just do our usual thing where we split an equilateral triangle has 60-degree angles in it, which is great because that means that half of it would be at 30, 60, 90. So if this thing is half full, that means that if we're halfway up the side, that would be 25 right here. We'll be halfway up the 50 centimeter side. And if we do a 30, 60, 90 deal, 25 divided by 2 to get here, so we get 25 halves for that side, and then 25 root 3 over 2 for that side. So at the time that h equals 25 root 3 over 2. Awesome. Let's figure it out. Now you notice there is no standard volume formula for something this weird like a inverted equilateral triangle, but maybe we can figure out the volume. Because it's just it's a pyramid, or what do you call it? A prism, because this whole thing is constant triangular base. So the volume is just going to be the shape of the triangle at the end. It's going to be this area times the length of this thing, which is 600. So the volume, and I know I want to use volume because they gave me dV dt. So since I'm working with volume, I've got to have volume. The only way to get that is to start with the volume formula. So V equals the area of the concrete at the end, so this area times 2. Anyway, so that area is just going to be, see, this will be 25 because when it's half full, actually that's changing now. And I have I have H and I want to know dH dt. So maybe I should figure out the area of this triangle of the concrete in terms of H. Because if it's H here, oops. If this is H, then this little distance is going to be H over root 3. If that little distance is H over root 3, then this whole width is 2H over root 3. So the area of this end, the area of the triangle, is just going to be 1/2 base times height, which is going to equal 1/2 times 2H over root 3 times H again. 2's cancel, so I just get H squared over root 3. Alright, so that's the area of the base. So the volume is just going to be the area of that triangle, which is H squared over root 3, times the length of this whole trough, which is 600 centimeters. And everything here is in centimeters, so we're all good. Alright, so at this point it looks like I've got something I could take the derivative of. And it's a pretty easy one. I just get, do it up here, I'll just get that dV dt equals, now the 600 over root 3 is just a constant. And then I got to multiply by 2H dH dt. Alright, so hopefully that's not covered up for you. So dV dt equals all that stuff, and they're asking for dH dt. Oh man, so I got to divide both sides by 600 over root 3 2H. Alright, so at this point it just becomes an algebraic nightmare, but hopefully you guys know how to do that stuff pretty well. So we'll get that dH dt. So I'll just invert everything. So root 3 over 600 gets rid of that stuff, and then I got to divide by 2H. And then I'm still got a dV dt to worry about. Alright, so at this point I can just plug in. I already figured out that H equals 25 root 3 over 2. Obviously you're going to want a calculator for this one. I figured out that dV dt, where they gave me that, equals 1,000. So when you plug all this junk in, I got an answer of 0.067 centimeters per second. Pretty exciting stuff. But as you can see, the trick to this one was that there's no standard volume formula for a triangular trough. You just have to sort of invent one by taking a cross section of the trough and then multiplying by the depth of that trough. And then beyond that, we just use the usual 30, 60, 90 tricks to get everything in terms of H, since the problem was given. They asked us for a dH dt, and they gave us some stuff where it looked like we needed to work the whole problem in terms of H instead of base. Alright, so that's related rates. This is how gnarly they get. There's obviously an infinite variety of problems that a teacher could ask. I obviously cooked up some weird ones here, but the point is that the process is always the same. Look at the givens, name them as variables, and then just look at all your letters and say, huh, if only I had a formula that had all those letters in it, or that if it doesn't have those letters in it, when I take the derivative, it'll have all those letters in it, and all the dt's and everything I need. At that point, just make sure you can take everything and jam it in there, plug and chug, and you're good to go. But, you know, practice, obviously. You don't want to be stepping into the test trying these for the first time after watching this video.